So we have seen earlier that how like to add numbers and stuff like that. When you add like two numbers, there is a possibility of having an overflow. So what's exactly overflow means? Meaning that the product or the sum, for instance, is greater than the available number of bits. So suppose that I'm asking you just to add two decimal numbers. Let's say 90 plus 90. So 90 plus 90 is 180. So you need actually 3 digits to write 180. But if I'm just 90 plus 90 and the output is in 2 digits only. So how you will write that? The 1 will be excluded. Then you will just write an 80. You need to come up with a strategy is how to deal with an overflow. For instance, you might say, instead of 180, instead of just 80 to be written in these 2 digits, I would choose to be a little bit much more closer to the correct answer, meaning that I will just choose the largest number that I can write in 2 digits. In that case, you will choose 99, for instance, and so on. There are like some strategies that you can actually think of, but this is one of the strategies. So with the MIPS also, if you were to write this as unsigned, especially when you deal with the unsigned numbers, because this is also another important thing, if the last bit is just referring to a sign or not. So just using the U, add U or add immediate U and so on and so forth. Other language like Fortran and so requiring raising an exception or interrupt. So using like in the MIPS add or add immediate and sub all of these instructions. With this kind of overflow, or we have an interrupt. So I may save as an example in my program counter, what is the exception program counter register, meaning that as soon as I'm going through the instructions, now while dealing with one of these instructions, I just found an interrupt, a problem, an error. Then I can send an interrupt, yes, but when to handle that interrupt? Should I handle that momentarily or later on and stuff like that? One of the strategy is just to save the address of that particular instruction into my program counter, so I can go back to that particular address as soon as I finish the task that I am working on, if this was the case. Or I might jump to a predefined, like as an example, handle address, or whatever the strategy that we were to choose in our case. And this is, by the way, can be implemented by ourselves, meaning that we can actually implement that using the Verilog language on the FPGA. Okay, so let's see how we can think of a multiplication, meaning that we would like to multiply two binary numbers with each other. So first, we need to see the steps that we are going through, but not only that, we need also to think about the implementation, how we can implement actually a multiplier. In that sense, if we were to do a multiplier inside the FPGA, how this would be built, or how we can think about exactly what we are doing in terms of the steps, mathematical steps, and how it is transferred to a certain particular implementation. So let's go through this journey together. So now I have two numbers, this number and that number. I would like to multiply these two numbers together. That number, we will refer to that as the multiplier. That number, we will refer to that as the multiplier. Okay, so how we can do that? So it will be 1 multiplied by all of these. 1 multiplied by 0 is 0. 1 multiplied by 0 is 0. 1 multiplied by 0 is 0. 1 multiplied by 1 is 1. Okay, so this is the number here. Then we'll shift to the left. We'll get the next number, 0. 0 multiplied by all of these will be all zeros. So I have here all zeros, but I have to take into consideration that also that number has to be shifted to the left. Then go to the next number, 0 multiplied by all of that is zeros, but again, I have to shift that to the left. And then we'll go to the other number, which is 1. 1 multiplied by that is just the same number as you can see here, but I'm just shifting to the left. And what I would do at the very end is just adding all this together. So 0 would be 0, 0 plus 0 is 0, 0 plus 0 plus 0 is 0, 1 plus all zeros is basically 1, all zeros is 0, 2 zeros is 0, and then 1. So this is the product, and I'm referring to that as the product. So I have a multiplier, multiplicand, and the product. But if you look closely at whatever the steps that we are doing is not but shift and add. Let's go again and see what is exactly happening. First, I look at the number that is here. If it is 1, I will take that number as it is and allocate it in my product. Then go to the next number. So I'm shifting that number, going in that direction. I'm going to the next number. If it is 0, so actually I don't need to do anything, just shift. Because if I remove all of these zeros and I'm just adding this with this, will give me the correct number. The only important thing is that to add it in the correct place. So I have to add this actually with these zeros. This is the correct place. This is what I need to handle. Meaning that when I will face a 0, what I need to do is just shift left, in this case, the number. And I don't have to add, because adding these zeros did not make any changes, correct? So I don't do that. And then go to the next one is zeros. Then just shift the numbers without adding anything. And then if it is 1, I will take that number as it is and then shift it and then do the addition. Let's try to look at that particular implementation scheme. We have here the multiplier. So this guy, 1, 0, 0, 1 will be here, but it will be written in 32 bits. The multiplicand will be here. It is written in 64 bits, and it will be in the first in the right 32 bits. So basically 1, 0, 0, 0 will be here, and I will keep shift left. As soon as this 32, of course, will be shifted another 32. That's why I have here 64 bits. And then this is an ALU that will add this with the results of my product. So suppose that I'm adding this with this, and then the results is that, then I'm adding with this, then the result is that, then I'm adding with this, and so on and so forth. Just keep adding. Yet adding the product. So as you can see from here, that this, I will double check about this number. If this number is 1, then what I need to do is the shift and also adding that number to whatever I had in the product. But if that, then I will shift right to go to the next number. The next number is 0. If it is 0, I don't actually need to do this addition at all. What I need to do is just shift that and then shift this to the next number, and so on and so forth. So how this exactly happened, let's see a nice animation to represent that. So here we have all of these, the multiplicand, the register, ALU, and the product registers. All of these are 64. This is the only one that is 32 bits. Let's see like how it works. The multiplication operation starts with the product initialized to 0, and this does make sense. So whatever is here is basically all zeros. And then the 32-bit multiplicands start in the right half of the multiplicand register. So here, the very first 32 bits, we will write just the multiplicand at that particular place. Then I have here a control test. I'm checking the very first bit in my multiplier to determine if I need just a shift or I just need to do the shift and the addition in this particular case. Since this is only 0, then I don't have to do an addition. The only thing that I need to do is just shift this to the left and shift this to the right. See it again? This is 0, it was 0, so just shift that to the left, shift that to the right, and now I'm checking the next number. So this kind of shift is the same thing as we had earlier with a shift in the multiplication, because I don't have to do any addition in that case, correct? It's just shift. Then go to the next one. I would check that this is actually 1. Oh, if this is 1, so actually I need to do the addition between the multiplicand and the previous product and update the product now with the new results. So this was 1. So again, you will take whatever is here, add it with the previous product, and then now update my product. Again, this will be shift to the left, this will be shift to the right, and just like repeat that operations all the way until I finish my numbers in this particular case. Also, I can represent that in terms of a flow chart. So I have here a certain algorithm that I have implemented in a flow chart. And by the way, one of the very nice things in Verilog that actually you can write a Verilog program just using a flow chart. You don't need actually to think in details about how it is exactly implemented, but you need a flow chart and then follow the flow chart. Then you can actually implement a design like that or a different design, but at the very end, it's doing exactly the same exact process that you are interested in. Let's go over that. It's just I'm testing if the multiplier, if it is 0 or not. Because if it is 0, I don't need to add. What I need to do is just shift the multiplicand and shift the multiplier. One would be to the left and the other would be to the right. And that's all. And then we'll keep doing that to the next one. If it is 1, then what I need to do before the shift, just add the multiplicand to the previous product and then do again the shift and so on and so forth until you finish the steps or the multiplication. Also, just in terms of hardware, this is one of the options, but also another way to do that with an optimized multiplier, that instead of having this as a 64 and having a multiplier, they have this as a 32 and they don't have the multiplier registered by itself. The multiplier actually would be written here, and instead of having a 64-bit ALU, I will have a 32-bit ALU. So this will do exactly the same things. The only difference in terms of the space is basically how much is the area consumed. In this particular implementation, the area, of course, is less and so on and so forth. And this would come with experience with how to write an efficient Verilog code versus like a non-efficient Verilog code. But both of them will do the exact same things in terms of the multiplication. You can also have a faster multiplier. For instance, if you were to have several multiplications performed in parallel, you can have actually multiple of these adders and with different like ALUs, then you can actually have things a bit faster and so on and so forth. So how we would be able to implement something like that in MIPS? Suppose that I have MIPS, I would like to multiply whatever in RS with whatever in RT. So I write multiply RS RT or multiplied unsigned RS RT. Interestingly, I can have up to 64 bits. The product can be up to 64 bits. In that sense, I have a register called high and a register called low inside my register. So two of these slots, one would be called high, another one would be called low. In the high, it will save the most significant 32 bits. In the low, it will save the least significant 32 bits in that case. So suppose I would like to see actually whatever is written in high or whatever is written in low in one of my registers. Suppose like I choose S0 or T0 or whatever. So I can say, okay, move from high to our destination. This our destination can be S0, can be T0, can be T7, whatever the destination I will use or I will choose. Then move from high to whatever in high will be basically copied in RD, whatever the R destination register that I will choose. I can also, instead of high, I can use the low. So I will use move from low to the RD, and again, we'll see the same thing. Suppose that I have used this instruction in the MIPS, mul RD, RS, RT. Since this RD is only 32 bits, so it won't be able to hold the whole 64 bits. So will it hold the very first least significant 32 bits, or will it hold the most significant 32 bits? Actually, it will hold the least significant 32 bits of the product. So basically, in that sense, whatever in this RD will be the whatever is exactly in low in that particular case. So this is just in the multiplication. Try to go even further with the division, how we would be able to do a division between two binary numbers, and then how we would think about the implementation. Suppose that this is, I would like to divide this number with this number. We will refer to that as the dividend. We will refer to that as the divisor. And then the results, we will refer to that as a quotient. And then at the very end, we will refer to whatever I received here as the remainder. How I will begin this division? First of all, I look at that number. I found that that number is greater than that number. So this divide by that, it will give me only 1. Remember that this is just binary. So the output I'm expecting is either 1 or 0. If this is greater than that, I will have here 1. And then 1 multiplied by that, I have this here, 1, 0, 0, 0. Then please do the subtraction. 1 minus 0 is 1. All of this is just 0. So now I have 1. Just get the 10, the 0. So now I have 1, 0. 1, 0, divide by that number. This guy is basically less than this guy. If it is less, the quotient will be 0. Of course, 0 multiplied by that is all zeros. This minus the zeros, it will give me the exact same number, so I don't have to do all of that here. Then just get the next number. It will be 1, 0, 1. The same thing is 1, 0, 1, divide by that. This is less, so the output or the quotient will be 0. Then get the next one. It will be 1, 0, 1, 0. 1, 0, 1, 0, divide by that. Oh, this is basically greater. This one is greater than this. So I will have here 1. 1 multiplied by this is that. And if you do this subtraction, you will get 1, 0 at the very end. So now I have the remainder. So as you can see from here, also, it's again shift. But after I check if that number is greater than that number or not. Because if it is greater, then I have to allocate here 1. If not, I have to allocate here 0. But this is because in advance, I know that in my brain. But in implementation-wise, I actually need to do the check first, correct? I need to do the check, meaning I will get the results, yes, or the remainder, and then check, because this is the remainder in this case, after the subtraction. I need to check if this is greater than that or not. And if it is greater, then I would do something. If it is not, I will do another things. Or I might actually revert to that because I need to know in advance if this is greater than that or not. I can do this and check and stuff like that. So again, this can be implemented with a similar implementation here. We'll have a 64 bits. We will add the divisor here in the left 32 bits. We have a 64-bit ALU. And then the remainder will be here. And then I will have here the quotients which hold the 32 bits. So let's check this here in the animation, how things are going. So again, this and this and that, they are all 64 bits. This quotient is 32 bits. As we mentioned, the divisor is placed in the left half of the divisor register. So basically the left half here. The dividend is placed in the remainder. So the dividend is placed here. And then the quotient, of course, the very first thing is just 0. Then I will subtract the divisor from the remainder, and then check the results. Because I don't know in advance if it is greater or not. I will check the results. If the results is negative, so I know now that actually it was like that. If it is positive, then I have to do another things, as we will see right now. So if the results is negative, then the remainder value is restored by adding the divisor to the remainder. Because now if it is negative, so this means that I shouldn't have done this actually. I have to return everything as it was. So I shouldn't have done like this particular process, just return everything as it was. So a negative remainder indicates that the divisor did not go into the dividend, and then Control Shift quotient 1 bit to the left, and then place 0 in the least significant bit. So the quotient is still now 0, shift left and add here the 0. And then the divisor, we are going to the next one, is shifted right by 1 bit. And of course, the divided operations repeat. Again, the divisor is subtracted from the remainder. And then the new results will be in the remainder. We'll check the same, if it is positive or negative. So we have seen what would happen if it is negative, but if it is positive, that means the divisor is smaller or equal to the dividend. Then actually, we will allocate now 1 in the quotients. We'll do the shift, and then we will allocate now 1 in the quotient. And then shift right that one, the divisor, and this keep repeating the operation until you finish the whole division number. This is also can be implemented using this flow chart. Again, I will subtract the divisor from register from the remainder register, and then we'll place the results in the remainder and check if it is greater or equal than 0 or if it is less than 0. If it is greater than 0, again, we'll just like put the 1, of course, right, most bit to the 1, and then we'll do the shift, and then shift the divisor, then again repeat. But if it was less than 0, so this means that I should not have already done that. This was like a mistake. So please, I just need to return everything as it was, restore the original value and stuff like that, and keep repeating until you finish the whole number. Also, this can be implemented using an optimized divider. So instead of having this as a 64 bits, we'll have this as 32 bits. Also, the ALU will be 32 bits instead of 64 bits. There is no actually quotient. Actually, the quotient will be held here in the remainder. And we'll have like a control, of course, that will either shift right or left, depending on whatever the stuff that we would like to hold in this particular case. Unfortunately, we can't do the pipeline and parallel division since we have a subtraction, and this is basically conditioned on the sign of the remainder. So I won't be able actually to do this in parallel. Unfortunately, with the division, I can't do this in parallel. With the MIPS division, it is the same kind of way that we dealt with the multiplication. The difference that here the high, it has the remainder. The low, it has basically the quotient. So if I write div rs comma rt, I would expect that in the high we'll have the remainder, in the low we'll have the basically the quotient. I can use the div or div unsigned. Also with the MIPS, no overflow or divide by 0 checking. This is just happen in the software step. It should perform the check if required. However, if we were to build everything by ourselves in the Verilog, we can actually build a module that would check all of these things and will do a certain actions depending on whatever we need. Since we are building the microprocessors from scratch, we are not depending on any other processor that is there. We are building the processor by ourselves in the FPGA. And again, if I would like to read whatever is in high or in low in a certain particular register, I will use either the move from high or move from low. I may say move from high and then write a certain destination register, or move from low and then I write a certain destination register. Suppose that I know exact numbers in this particular case. All of this is just like representing multiplication division, but all what we have mentioned is just integer number. Now we need to switch the gear a little bit into another way of writing the number, which is basically floating points. So now we can write fractions. We can represent numbers in scientific notation. So instead of having like this in the decimal, we can have this in binary. 1 point some fraction multiplied by 2 to the power of something. As you can see from here, if I multiply by 10 to the power of -4 or any number multiplied by 10 to the power of -2 or 10 to the power of negative something, it is not but moving the point to the left by that number, correct? So if I multiply a number by 10 to the power of -2, so this means that I'm moving the point to the left by 2. If it is multiplied by 10 to the power of 2, so this means that the point is moving right by 2 and so on, correct? Because I'm speaking about the base 10. However, if I'm speaking about a base 8, for instance, so it will be that number multiplied by 8 to the power of -2. What does that mean? Meaning, again, with that octal number, I will move the point left by 2. Or if it is 8 to the power of 2, so it will be moving right by 2. 8 to the power of 3, moving right by 3, and so on and so forth, correct? But with exactly the same concept, if I'm dealing with binary numbers, I would multiply it by 2 to the power of something. So 2 to the power of -3, what does that mean? Meaning, again, that whatever the number that I have as a binary, I will move the point 3 steps to the left, or 3 points or 3 digits to the left. If it is 2 to the multiplied by 2 to the power of 3, so that point will be moved to the right, and so on and so forth. So this kind of floating points, like in C, I can represent that by float or double, for instance. But in order like to write a numbers and then we can represent that as a floating points, we can either have our own standard that we will build with our own design, or we can follow others' standards, correct? In that case, there is a famous IEEE format standard that actually we will follow in writing floating point standards, and it has a single precision in 32 bits and the double precision in 64 bits. So this means that they will tell us exactly how they will decode the zeros and ones in a way that we can read it as a floating point. So how is that? Here's an IEEE floating point format. And this is whatever the format that they have already choose. So they already chose that particular format, and what we need to do is just to follow that format. However, we can actually create our own format if we were to build like something by ourselves or whatever we are interested, or maybe in the future in another company that you are working with or stuff like that, you may have actually another format that you will follow by yourself. Suppose that this is the IEEE format. It tells you like, okay, this guy here is 32 bits if I have a single precision. So it will be 32. Or this guy will be 64 if I have double precision. Okay. Further, how actually each one is decomposed to several parts. The very first bit is the sign bit. This sign bit will be equal to 0 if it is non-negative number. It will be 1 if it is negative number. Then I will have the next bits, 8 in case of single, 11 in case of double, that will represent something called exponent. Then the next bits will refer to that as a fraction. The fraction will be 23 bits in case of single. It will be 52 bits in case of double. In the single format, if you add the 23 plus the 8 plus the 1, you will get the 32. If you add the 52 plus the 11 plus the 1, you will get the 64. Okay, so these are zeros and ones. How we will read it. As you have seen earlier, I can write the zeros and one, and I can tell you, I can ask you what that number is, given that it is unsigned. You will read that as a certain number. I may say, no, that number is signed, so you might read it differently. I may say that this is actually 2's complement. You will read it even different. I may say that this is 1's complement. Again, you read it another number. I may say it that this is actually in an IEEE format. Then you will read it again differently. But how you will read it, here is their rule. They say that that number that you will read from all of these zeros and ones is following this formula. Is minus 1 to the power of the sign bit. So whatever is here will be here. If this is 0, this will be 0. If this is 1, that will be 1. Then will be multiplied by 1 plus the fraction. Fraction, whatever is here. So I will put whatever is here, here, and 1 plus that fraction. So this means that that number will be read as a fraction. So if it is 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, whatever, all of this will be read as a fraction. You can think of this if we were to work with decimal. If in this fraction it is written like 9,999, it is not actually 9,999. It is 0.9999 because I'm looking at that number as a fraction. So 1 plus whatever is the fraction, and we will refer to this 1 plus the fraction as something called significant. So the smallest of this significance can be 1, but it won't be able to exceed than 2. So 1 point something fraction, but it can't go up to a 2 since we are just still working with that kind of binary number. And then multiplied by 2 to the power of exponent. Exponent is whatever is here, minus something called bias that we will explain shortly. But just take it as it is right now. 2 multiplied by the exponent, which whatever the number that I have here, minus the bias. Bias, this is actually the IEEE researchers that shows that. And this can be another things in any other format. But for instance, with the single precision, the bias is 127. With the double, the bias is 1023. Basically, how did they calculate that? Or moving forward, if I give you a certain particular, another number of exponent, how you will be able to calculate the bias? Here is the way that you will do that. It is 2 to the power of this 8 minus 1 and then minus 1. 2 to the power of the 8 minus 1, so 2 to the power of 7, it will be 128 minus 1 is 127 basically. And that's why it is 127 here. So if I were to give you like an exponent, let's say like 5 or 6 bits, so you know now how to calculate the bias. Suppose that I would like to see how they calculate that for the double. It is the same exact concept. 2 to the power of the exponents in the double, it is 2 to the power of 11 minus 1 and then minus 1. If you do that, 10 to the power of 10 is 1024 minus 1 is 1023. So now we understood how to calculate the bias. So as soon as I will see the zeros and ones here, I will be able to know what is the number that they are referring to in terms of their format. Okay, so that's fine. We'll take some examples later, but before we do that, we need actually to see what would be the smallest value that we can represent using that format and what would be the largest value that we can actually represent using that particular format in terms of the single precision, and then we'll see that on the double precision. So before we know how to calculate the smallest value and the largest value, we are just giving you here an information that the exponents, all zeros and all ones is reserved, meaning that you can't use here all zeros. You can't use that. It is reserved, and we'll show you later on why this is reserved or to what is exactly reserved. Also, all ones, it's also reserved. You can't use that. So given these two restrictions, what would be the smallest value that you would be able to get from a number like that? Okay, so what is the smallest value? If these are all zeros and I can't get that, so let's take just the one digit that is larger than that. What would be that? It's all zeros except this will be 1, correct? So all zeros except that will be 1. So this will be my exponent. But actually, I would like to calculate 2 to the power of the exponent minus bias, exponent minus bias. So I would call or refer to that as actual exponent. So actual exponent will be the exponent minus bias. I know that actually the bias in the single precision is 127. So 1 minus 127 is minus 126. So I know now that this is not but minus 26. Okay, how about the fraction? What would be the smallest fraction? If I'm giving you all of these and I'm asking you what would be the smallest fraction? All zeros, correct? Just all zeros. This will be my smallest fraction. So the smallest fraction is all zeros. Okay, so now I need to build my number. So it is x equal to minus 1 to the power of the sign, and then multiplied by 1 plus the fraction, multiplied by 2 to the power of exponent minus the bias, correct? Exponent minus the bias is already there. So it will be 2 to the power of negative 126. So it is 2 to the power of negative 126. 1 plus the fraction is 1 plus all zeros, or 1.0000. It's just 1, so it is only 1. Minus 1 to the power of the sign, it depending on the sign. If the sign is positive, it will be positive. If it's negative, it will be negative. So I can just write that as plus or minus. So it will be plus or minus 1 multiplied by 2 to the power of the actual exponent. How about the largest value? The largest value in the exponent, I would like to take all ones, but as we mentioned, it is restricted. I can't get that. So what will be just the largest number that is less than that will be all ones except this will be zeros, correct? And this is what I have here. How I will read that one? This, if you read that number, it is 254. 254 minus 127 is 127. Okay, so this is actually the actual exponent. It's just the exponent, again, minus the bias. What is the largest fraction that I would imagine here? This is binary numbers. If it is decimal numbers, the largest fraction will be 9999999 all 23 times or 52 times, correct? But this is just a binary, so what would be the largest? All ones, correct? So the fraction will be all ones. So now actually the 1 plus the fraction is not but 1.01. So again, x is minus 1 to the power of s, 1 plus the fraction, 2 to the power of exponent minus bias. 1 plus the fraction is 1.111 all the way. 2 to the power of exponent minus bias, 2 is here. Exponent minus bias is here, so it is 127. And then it's just plus or minus depending on the sign of the s. Let's try to do the same exactly thing, but with the double precision. We would think exactly the same. The only one difference is the value of the bias. Let's see how we can do that. Again, all zeros are reserved, so we'll just get the smallest as all zeros, except the very first one, it will be 1. So the actual exponent is basically 1, which is here, minus the bias, which will give me that number. The fraction, again, all zeros, so the significant will be 1 plus the fraction, which is that. And then the whole number will be the significant, because actually this is the significant, multiplied by 2 to the power of actual exponent. Actual exponent is not but exponent minus bias, which is exponent minus bias is that. So significant multiplied by 2 to the power of actual exponent, which is that one, plus or minus depending on the sign. What is the largest value? Again, I can take all ones, so I will take all ones except the very first as 0. So that number is 2046 minus the bias is giving me that number. What is the largest fraction that I can get is all ones again. And then the significant, it's 1 plus that, so 1.1111 all the way till the very end. So it will be just plus or minus 1 plus the fraction multiplied by 2 to the power of the exponent minus bias. And the exponent minus bias is actually this number, which is that number here. So this is the number, of course, corresponding number in decimal, and we'll see later on how we can actually present that also in this. So suppose that we actually are interested to see, like for instance, what would be the floating point precision? So meaning the single precision, how many decimal digits we will have as a precision in the single format and in the double format, and how we can calculate that. With the single format, so we have actually 23 bits in the fraction. So we can go up to all of these 2 to the power of that. So basically take the log, so it will be 23 multiplied by log 2, so it will be 23 multiplied by 0.3, it's 6 decimal digits. So this means that with the single precision, I can go up to 6 decimal digits. So I can differentiate between 2 different numbers by 6 decimal digits. So if we were like to be very precise, I would believe like 6 decimal digits hopefully will be enough. If it is not enough, you can use actually the double. So it instead of 23, you will have here the 52. So 52 multiplied by log that, it's 52 multiplied by 0.3. We can go up to 16 decimal digits. So you can actually differentiate between 2 things or 2 numbers with 16 decimal digits, which is, of course, very high precision in that sense. So suppose that we have an example that asking you to represent the minus 0.75 in an IEEE format. So at the very end, I would like to see this in zeros and ones according to the IEEE format. So how to get something like that for instance. Or if I were to give you this, how to get this back also, you can get the other way around. So you can have the number and then going back to the IEEE format, or having the IEEE format and going back to the number. It's just like the opposite, basically, process. So the question here is asking you, please represent minus 0.75 in binary format, given that, for instance, we need a single precision, as an example. How we would think about that? First of all, we need to see how we can write that in binary. So 0.75 multiplied by 2 will give me what? Will give me 1.5. We will write the integer here and the fraction here. And again, multiplied by 2 is 1. The fraction is 0. So actually, 0 multiplied by 2 is 0. So we can just stop. So at the very end, 0.75 is basically 0.11. 11 because here I have the 1, 1. So now I have 0.11. So we know now how to write 0.75 in terms of binary representation. Of course, this is minus. So this is, you can think of this as just a minus. How now I can build the IEEE format from that number? Remember that with the IEEE format, we have S, and then we have the exponent, and then we have the fraction. So we need to know like how we can do that. Remember that my x is written like that, minus 1 to the power of the sign, 1 plus the fraction, 2 to the power of exponent minus bias. And we mentioned that actually the actual exponent is equal to the exponent minus bias. That means that if I have this, the exponent, which should be here, is basically equal to what? Its actual exponent plus b. Correct? Okay, so how actually we will get all of these information from just that number? First of all, we need to write that number in the format that is 1 point something multiplied by 2 to the power of something. Because this is what we have here. 1 point something multiplied by 2 to the power of something. This is what we have here, correct? This is just multiplication by that. Okay, so let's do that. How about writing this that way? 1.1 multiplied by 2 to the power of negative 1. If this is equal to that, the answer is yes. Why? Because 2 to the power of negative 1 is not but moving the point actually 1 to the left. So when we move the point 1 to the left, we'll have 0.11, which is basically equal to that. Because if you recall, I mentioned 2 to the power of something is just moving the point, either right or left. It's exactly as in decimal when we multiply by 10 to the power of something, correct? So now we have everything. How? This one is basically that one. The fraction, 0.1. So basically the fraction is just 1. 2 to the power of negative 1. So this is negative 1. So the actual exponent is negative 1. So apply that here. So basically the exponent now will be equal to minus 1 plus the bias, which we already knew in the single precision is 127. So actually the exponent is 126. That's all. So in the exponent, now I hope that I will write here 126. In the fraction is just 1 and all zeros. And the sign is negative. And if you recall, if the sign is negative, so basically S is equal to 1. So here, S is equal basically to 1. But of course, I can't write 126 in decimal. I have to transfer 126 to binary. So basically, 126 need to be written in binary, which will be like that. It will be 0, 1, 2, 3, 4, 5, 6. I think all zeros. I hope that I am not mistaken. But as again, this will be here. So that means that I will write actually that number here. And this will be my number. So that S will be just 1. And this is S here. So 1 and that number and then the fraction. And that would be the case. If I were to write the same thing, but in double precision. Okay, so the only difference with the double precision will be what? Will be the exponent, correct? So instead of having this 127, so basically this guy in the double precision will be equal to -1 plus 1023. It will be 1022. So that means that this 1022 basically will be here instead of 126. But also the exponent will not be written in 8 bits. It will be written in 11 bits in that case. And the fraction, again, will be the exact same thing, 1 and all zeros. Again, this is 1. Here's the exponent, which is 1022. Here's the fraction, which is all ones and all zeros. How we will write this in binary? If you do the translation, it will be the beginning zeros and the very first zeros, and then I guess all ones in between. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe another one or so. So it will be something like that. At the very end, the idea that you put actually is the binary there. So we have represented now the -0.75 in single format and in double format. Suppose that you have now 5.2 and you need to do the exact same things, but instead of 0.75 or -0.75, you have now 5.2. So you have an integer part and a decimal part. How you will deal with that? 5.2, we know that 5 actually is 101, correct? In binary, we know that, but 101 point here. 0.2, how we will represent 0.2 in binary? This is what we will calculate. Again, with the same concept, 0.2 multiplied by 2. What is that? Is 0.4. So the left to the point is 0, and then the number is just 0.4 multiplied by 2. Again, 0.8 multiplied by 2. Now I have an integer. It will be 1.6. 0.6 multiplied by 2 is 1.2. Multiplied by 2 is again 0, and then 0.4 multiplied by 2, and so on. So I don't want to continue, because basically, if you look closely from here, I will just keep repeating. It will just keep repeating, correct? So it will be 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and so on. So I don't have to repeat. Okay, so if this is the case, then I just need to write that in terms of the decimal. So it will be 0, 0, 1, 1, 0, 0, 1, 1, and so on and so forth. So I have my number here right now. The same concept exactly. I would like to write that number in a representation that 1 point something multiplied by 2 to the power of something. Correct? This is what I would like to do. I have the number, but it has to be written in this scientific format. 1 point something multiplied by 2 to the power of something. Okay, so this is basically, if you think about it, this is equivalent to 1.0100110011 and so on, multiplied by 2 to the power of 2. Correct? Because basically, if you think about these two, is moving the point actually by 2. So it will be 101 point all of these. 101 point all of these. So they are equivalent, correct? So after that, it's not the same exact steps. We now know that this is the fraction. This is the fraction. These two is the actual exponent. How we can get the exponent? From that, it is 2 plus 127, which is 129. So we need to write 129 in binary. It will be 1 and then and then 1 like that. So now we can easily build my format. S exponent and then fraction. What is S? This is positive number, so basically I will have this as 0. What is the exponent? The exponent is not but this number. So I will just take that number and put it here. What is my fraction? My fraction is basically that one. So I can actually take also that one and just copy it here. 0, 1, 0, 0, 1, 1, 0, 0, 1, 1. You don't have, of course, to write that 23 times or 52 times. I would understand that this is basically just repeating. So now I have this number, and this is basically represent that number. And I can do the exact same thing if it is double precision. Instead of 127, I will go with 1023. Or if I'm giving you a totally new format, you can actually calculate the bias from the exponent, the number of bits of the exponents in that particular other format, and you need to apply the same exact steps.